Let us start now. Let me revise what we ended up in the last class. That is about Lieberman nitroso test. Okay, I told you that HNO2, HNO2, which is prepared from NaNO2 and HCl, will be responsible to generate NO plus as an electrophile. And this electrophile, if it attacks from ortho position or from para position, ortho or para position, you will get this form. Okay.
Okay.
So this would be quinone monooxide because it will undergo tautomerism. So this hydrogen will shift here, double bond will shift here. That way you will get an oxime. So quinone monooxide. Quinones are usually colored, and the first color you will see is green. And in acidic medium, if at all I keep it, because you are already using an acidic medium, you can expect this, that it will become OH2 plus. This can be relieved and you start gaining a positive charge on nitrogen. And that is where the phenol will make another ES reaction. So you will get second product, which is indophenol, which is red color. And thereafter, if I use a basic medium now, or if you take this indophenol and add it to basic medium, OH minus will take H plus from here, convert into this O minus, which will appear blue color. Okay, this is called GRB test, or green, red, blue Lieberman nitroso test. I told you that Lieberman nitroso test is used in two cases. One is to detect phenol. Second one is to detect secondary amines. Okay.
Okay.
When it comes to secondary amines, we'll discuss there again. Right. Now, going into Fry's rearrangement. Fry's rearrangement is a case where you have an ester group with respect to the phenyl substitution, and then we use AlCl3 and heat, Lewis acid and heat. What you can expect is this one. The oxygen present here can get attached with AlCl3, gets more like a leaving group here. Now between these two bonds, if it breaks, you will get RC double bond O. This is called acyl carbocation, ACYL. Okay, it's called acyl carbocation. Acyl carbocation is very stable because it can make a resonance stabilization like this. Okay, because it has a lone pair here with a plus charge. So this lone pair can push here. So I will get this as RC triple bond O plus. Clear, beta?
Yeah.
So that's why it is an acyl carbocation stability which you will gain. Okay. And that's why the breaking would happen here. And because of which now there is an RC double bond O plus available as an electrophile for this group to react. So it can attack from ortho position, it can attack from para position. Okay. What is being observed is that ortho is major at high temperature, para is major at low temperature. Okay. Now, there is
Okay.
not much of a detailing on that, but I would suggest we would directly remember it. Ortho is the TCP here and para is the KCP here.
Yeah.
Okay. This is Fry's rearrangement. Next one, the most important reaction here is diazocoupling reaction. Diazocoupling is when you take phenol, react with diazonium salt. In diazonium salt, when the pH is around 8 to 10, okay, when the pH is around 8 to 10, from this position it will attack on nitrogen. So you'll get N double bond N here. Okay, so that would be an azodie formation. This will be an azodie formation. Clear, beta?
Okay.
And what you will get here, once you get an azodie, I mean, how do we get this azodie? See the mechanism. OH minus will take H plus from here. Why OH minus? Because I'm maintaining the pH a slightly basic medium. So OH minus will take H plus, creates a phenoxide ion. Phenoxide will make the ring highly activated, and N2 plus can be treated as an electrophile. So on this nitrogen position, from the para position of phenoxide, you can attack. As it attacks, you will see you will get a hydrogen N double bond N with a phenyl group. Hmm. And now OH minus can take H plus from here and push here to retain the aromaticity. Thereafter, it can take H plus from water to finally get into this azo form. This is called azo dye. N double bond N is an azo bond. So azo dye is formed, which is orange color.
Okay.
What are the important things to understand here? One, the color formation is due to the extended resonance. You see from here, if it keeps moving like this, due to this extended resonance, you will see color formation. Second, diazonium salt is unstable above 5 degrees centigrade. So that means the reaction should take place at a very low temperature. Okay. So that means it
Yeah.
is pH plus and N2 plus which has to be formed. Okay. In case if you go beyond 5 degrees. Correct. Second thing, this nitrogen has a positive charge. It can easily take these electrons onto it, get into a lone pair, and this nitrogen is the one which will have 6 electrons now, which will act like an electrophile. So students get confused that there is a positive charge at the central nitrogen, so that should be electrophile. No, because it is in resonance with the pi bond here, the electrophile is the last nitrogen. So that has 6 electrons. So that is a part which will act like electrophile. That's why the attack is happening on the last nitrogen, right? Next.
Yeah.
So pH N2 plus is a weak electrophile. It will normally attack highly reactive aromatic compounds like phenol and aniline. Okay. It will normally attack highly reactive aromatic compounds like phenols and anilines. Got it?
Yeah.
Now, phenol, if you react with pH N2 plus with mild OH minus, this will give you a dye. Okay. So that is if you have phenol here like this, correct? So let's say I have a phenol on this side. So I'll get this as N double bond N and pH. This is the one which you will get, correct? Aniline
Yeah.
will also give you dye. But methoxybenzene, which means anisole, that is not giving it because this is not sufficiently activated. So to activate the electrophile, you need to have more withdrawing groups on it. So if you have something like NO2 here, which is strongly withdrawing, that will convert into a dye now. Okay. So that's why nitrogen, the para position from here will attack on the nitrogen. That's how you will get a dye. है ना clear beta?
Yeah.
Right. Next, you see, electron withdrawing groups increases reactivity of diazonium ion. So that means if you have methyl or nitro group here, nitro group if you have, it is electron withdrawing. So that means this N2 plus would start becoming more and more active for reaction. Next, if the cation exists in a mild H plus or OH minus, then nothing will happen. But if you have it in a strong alkaline medium, if you have a strong alkaline medium, OH minus will attack on this nitrogen, pi bond will shift on this nitrogen, and you'll get this N double bond N form. Okay. And OH minus could take H plus from here and get an extended conjugation here. And this particular acid is called diazotic acid. So which means you have to be very particular about the pH which you are using. If you are using a pH 10 to 12, then instead of making this reaction, the reaction will all the way go towards this side. Got it?
Okay. Yeah.
This reaction can also happen even with beta naphthol. So let's say if there is a beta naphthol here, okay, if there is a beta naphthol here, you will see uh, if I react with N2 plus, which has a withdrawing group, SO3 Na is there, correct? So then at this position, it can make a substitution at ortho position. Para position is not open beta, either this ortho or this ortho. Now,
Mm.
between these two ortho, this ortho is more activated. Alpha is always more activated than the beta position. So, therefore, at this position, you will have N2 getting added onto it, and this will become red color as a group. If it is alpha naphthol, right? If it is alpha naphthol, then this will go this time at para position, and that will be tango red color. So generally, this is the colors which you need to remember. If you have a beta naphthol, phenol, or aniline, these are the ones which are possibly giving azo dye. And the color for them is red, orange, and yellow. So remember it, BPA Roy. Okay.
Mm.
So these two, and these two are the colors combinations. Okay. What is the reactant? What is the color? Clear, beta?
Mm.
This is expected. Like you should know that which color and what is the reactant on it. Okay. Clear with coupling reaction, beta?
Yes, sir.
Right. Next, Gatterman-Koch, Gatterman reaction. These are very similar reactions which we have done it earlier for benzene. Here we are
Yeah.
doing it for phenol. That's it. So phenol, when you react with carbon monoxide plus HCl in the presence of AlCl3, at this position you will have an aldehyde, or this position you will have an aldehyde group. Okay.
Mm.
So now C minus can attack on H plus. It can remove Cl, and that's how it generates a carbocation, which is electrophile. And from ortho position and para position, it can attack. So you can get, here I've shown you ortho product. You can get a para product also similarly. Okay.
Yeah.
Same way, Gatterman reaction is when you take HCN in the presence of HCl, and this Lewis acid should be anhydrous AlCl3 or ZnCl2. Any one of
Mm.
that. So you take any one of this, react it. So what do we get? HCN will take H plus from here, right? You will get this form, which is an electrophile here. So this carbon will have an electrophilic nature. On that, the para position or the ortho position will attack on it. So you will get an imine form. Okay. Imines are
Yeah.
unstable in aqueous solution. So you will break it down, convert that into an aldehyde. This is Gatterman reaction. Okay.
Yeah.
Photo-Fries reaction is, instead of using an AlCl3, that means you are not using a Lewis acid, you are directly using heat. Reaction kind is same. So here C double bond O will come out as RC double bond O dot, and this dot and this dot. And here the dot will be again activated at ortho and para positions. You will get ortho product and para product. Okay, beta.
Mm.
Finally, if you compare the test of phenols, sodium metal test, it will give you a brief effervescence of H2. Okay, because hydrogen on the phenol, PHOH, this hydrogen is acidic enough. So it can release as H2 gas as it collects the electrons. Litmus test, it is, phenol is more acidic than water, which means it will convert into red color, blue to red color. Neutral FeCl3 test, this is the most important test for phenols. Usually, if I take any phenol, react with Fe plus 3 salts, any Fe plus 3 salts, Fe would accumulate all these phenoxide groups with it, 6 phenoxide groups with it. Okay. And FeOPH 6 times minus 3. This is what is going to be formed here. Clear?
Mm.
And as it forms here, you will notice that this group, even this one and this one, these all will give you red coloration with FeCl3. Got it? Why? Because these kind of keto groups will have more enol content. So percentage enol is more. So here, more than phenol, this reaction is giving that coloration because of the enol content. And you know that phenol will have 100% enol content more than its keto content. That's why it is offering to go in this forward direction. Clear, beta?
Yeah.
Right. Next, with bromine water here, so this would give a white PPT. With Br2 and H2O, it will give a white PPT, which we have
Yeah.
seen it earlier, 246 tribromo phenol. Next, with KMNO4 and basic medium, it will get decolorized and the solution turns brown. Okay, that is because of
Yeah.
the formation of quinone. This one, it will become benzoquinone formation. Correct? Because of this benzoquinone formation, it will turn into brown color. Clear, beta?
Yes,
Next,
sir.
if you have quinone, right? If you react that with ceric ammonium nitrate, which we used to do it for alcohols, here also it will turn into brown color. Correct? Acha, this is not just for quinol, it is even for phenols also. So even if you have phenol also, it will convert into quinones. So this can be used for oxidizing phenol into quinone form. Okay.
Yeah.
Lieberman nitroso test we have already seen, green turning into red, turning into blue. Hmm. So these are typically used as the test for phenols. Clear, beta?
Yes, sir.
Right. Okay. As much as the syllabus is concerned, this is how much you need to know from phenols. Clear? Now let's
Okay.
engage some time in understanding the type of questions that will be asked. Clear? Right. Just a minute. Right. Let's do some questions on phenols. Check. If you take phenol, react with CCl4 and NaOH, what do we call it? This is Remer-Tiemann carboxylation. Okay,
Yeah.
so that we can get salicylic acid. Correct.
Yes.
Kolbase is specifically used for aldehyde. Hmm,
Yeah.
correct. Sorry, Kolbase is also used for same salicylic acid, but using carbon dioxide, not CCl4. Okay. Clayton's reaction is something which will be coming, across again. While when it comes to Duff's reaction is something different, where we will have erythropine used here. So like this, again, we will be using this as a preparation in aldehydes and ketones. Okay, I'll just write it here though. CH2 6 times N4. This is called erythropine. And that when you react with this one and followed by hydrolysis, it will convert into an aldehyde form. That's it. Okay. This is Duff's reaction. Clear, beta?
Yes, sir.
Next. Heating 4-methyl phenyl acetate with AlCl3 produces what? Okay. 4-methyl phenyl acetate. Okay. So what do we have? We have a phenyl group which has a methyl group on it, which is connected with an acetate group. Clear? So O C double bond O CH3. Correct? This is what it meant. So first understand how the structure is. Is this clear? This is 1, 2, 3, 4. On fourth position, I have a methyl of
Yeah.
phenyl, of phenyl, which is connected to an acetate, CH3 C double bond O. Now, once that is there, this on heating is a Fry's rearrangement in the presence of AlCl3. Correct? So in
Yeah.
Fry's rearrangement, we learned that first we will get this as OH, and at this ortho position, you will get it as C double bond O CH3, and here we have methyl. Clear, beta?
Yeah.
Okay. Now, what is this one? This is called, at this much amount is called aceto, and this is overlapped is called as phenone,
Okay.
acetophenone. Okay, the name is acetophenone. And on the phenone, you will see 1, 2, 3, 4, 5, 6 this way, or I can go this way, that we have 1, 2, 3, 4, 5. Correct? So, what do we have here? If I go this way, I will get 1, 2, 3, 4, 5, 6. So I have, on second position, I have hydroxy. On fifth position, I have methyl. And then this is acetophenone. So which one is correct, beta? D.
Yeah.
The name is clear.
Yes,
Next.
sir.
Phenol can be distinguished from alcohols by using which reagent? Okay. We can't do sodium because both will give H2.
Yeah.
Alcoholic FeCl3, yes, this is all exclusively given by enols. Correct? So phenol is one kind of an enol. Clear? Bromine water both will be reacting. NaOH both will be reacting. Clear?
Okay. Yeah.
Because with NaOH there is no color change or anything which we can't see anything, right? Okay, so we can't do
Mm.
anything. Next, SOCl2. Okay. SOCl2, if you have it at allylic position, correct, usually it will go for allylic substitution here. So Cl will be attacking here, double bond will move here, and this group will go away. So what is the product you will get? A. The
Yeah.
Okay. So next one, which of the following does not react with NaHCO3? Okay, I told you that for NaHCO3 to react, we should have pKa value less than 6. Okay, benzoic acid will be definitely less than, in fact, almost close to 4 here. Any OH with one NO2 group, see, one NO2 group will be not sufficient enough. I told
Yeah.
you two NO2 groups should be present to have pH less than 6. So this will not react. At the same time, only phenol will not react. Picric acid means it will have 3 NO2 groups here, and pK value for picric acid is 1. So this will definitely give the positive reaction of bicarbonate test.
Okay.
Next one. Okay, this is Gattermann
Mm.
reaction. So if you have HCl in the presence of HCN, we just learned it, that
Yes.
nitrogen's lone pair will take H plus, generate the delta positive on carbon, and from here it will attack, and that will give you imine formation like this, OH and CH double bond NH. And this on hydrolysis will break this bond and convert this to aldehyde. Okay, so this is Gattermann
Yeah.
reaction. Next, OH minus. See, what's OH minus doing here? This is a tautomerism step. So this is just a basic tautomerism step. Here we have two hydrogens. OH minus can take away this H plus. It will have H with minus charge, double bond, double bond, double bond O. So this minus charge will pull like this, and pi bond will keep moving up. That way you will have O minus, double bond, double bond, double bond, and this one. Done? Correct. And
Yeah.
this on hydrolysis will convert into phenol. So by tautomerism, you will get phenol here. Okay. Clear?
Yeah.
Next. Phenol on aerial oxidation. See, if you make any aerial oxidation, what is the product that we will get here, beta? This one. Okay. Acha, question is, it is forming a colored product. Colored product is quinone. This one. Okay.
Yeah.
Why that is happening? Okay. Why that is happening is because of this one. Okay. This one, because of the strong hydrogen bonding which it has. Okay.
Mm.
The color formation, why it is, the question is why it is being colored formation. It is like an extended conjugation, correct?
Yeah.
But here the extension is because of this negative charge here and positive charge, sorry, negative charge here once and negative charge here once. So there is a movement of oxygen. Okay, so the reason is this one, hydrogen bonding. Okay, next, here H3O plus, what is the reaction that will take place? See, first here we will have double bond OH plus. Okay, because you are adding an acidic medium, first protonation will take place. After protonation, you will get this as OH. You know, double pi bond will shift here. This pi bond will shift on oxygen. You will get a double bond. You get a positive charge here like this. A double bond. Okay.
Yeah.
Thereafter, you can break this bond and push it here. So that we can get double bond with OH, and 6-membered ring will form here, and you get positive charge here now. Okay, and once you get that positive charge here, there is a hydrogen here, so you can remove that hydrogen to retain the aromaticity, and that way you will get this product. Done?
Yeah.
Which is option C. Done?
Yes.
Excess of HI, we learned it the other day. If you
Yeah.
take excess of HI, Can you break the phenolic oxygen group here? No, you can break here or you cannot break here. So the product here will be OH, here will be OH. Only this side the product will become PH2CHI. So which is option B. Done.
Yeah.
Next, I2 and NaOH. Okay, and I2 and NaOH. This is resorcinol. Now notice this resorcinol case here, beta. The same resorcinol, if at all I write it in terms of resonating structure, I can write this as double bond O, and here this way. Correct.
Yeah.
This is the enolic form which I can write. Okay, clear? Now,
Yeah.
when you write this enolic form, have you noticed that, I mean, ketonic form, this is the ketonic form when you write it. This is the active methylene group. And active methylene group, we learned that it will give a positive haloform test. Correct? So that is, if you have it this way, we have double bond O. First two iodides will come here like this. And later on, you will see that bond will break from here because OH minus will attack on this position. So this bond will break. So you will have this bond converting into double bond OH, and here we'll have two iodides with double bond O. And this on further treatment with I2 and NaOH, iodoform will happen at this position. At this position, you'll have iodoform. So you will have C double bond O, OH, and CHI3. Okay, and here also C double bond O, OH. Basically, OH will not be there, O minus will be present. So this is a product you will get. So you'll get 5 carbon, 1, 2, 3, 4, 5, and CHI3. Okay.
Yeah.
So what is a compound A, beta? If you do
Yeah.
hydrolysis, this is what you will get. Hmm? No, 5 carbon, right? Sorry. Where is 5 carbon we have here? There is a double bond already here. I should not have removed that. So option A. Hmm? Done.
Yeah.
Hmm. Check out on 12th now. Check. With AC2O here. Now, between NH2 and OH, which is a better donor group? Nitrogen is a better donor group. So therefore, the first reaction that will take place here will be from nitrogen end and not from oxygen end. So you'll get this as NHC double bond of CH3. Okay, this is the first product you will get. Clear, beta? So which is option
Yes,
C.
ma'am.
Hmm? If you do it for excess amount, then this will also undergo acetylation. Next, A is tosylation. So first we will have benzene ring connected this way with OTS. Okay, and OTS
Yeah.
is a very good leaving group. So that will leave and H minus will come. So that's how you will get this product. Clear, beta?
A.
Which is option C. Hmm?
Yeah.
Lieberman nitroso sequential changes in the color of phenol occurs as. Okay, what is the color that will take place here? Red or brown converting into green to deep blue. Okay, see, basically the green, uh, see, the first green color will not stay for a long time. So usually in books, the first green color, green, red, brown, this red and blue, this was the colors which we saw, right? So
Yeah.
usually this is not noticeable much. So first noticeable color is red and the next noticeable color is blue. Got it? So
Okay.
then that bluish deep blue color is the one which will slowly start defading into green again. So that is why this one is more appropriate for. Clear?
Yeah.
Mhm. Next. Phenol with HBr. Correct. This is an acidic group. This is an acidic group. So will you see much reaction happening here? Okay.
No.
No. So do you see any of the product forming here? None. Clear, beta? Right.
Yes, sir.
Next. Phenol in H2 and nickel at 20 degrees C. If phenol is being a strong activating group on benzene, so when you react with H2 and nickel, this will be the product that you will see. Only benzene will not make a reaction, but phenol will definitely make a reaction with H2 and nickel and reduces the pi bonds inside. With zinc dust, we learned that it will convert into benzene plus
Yeah.
ZnO.
So D.
So which one is that? D. Next, check out CH3COOH. This is peroxy linkage. Peroxy linkage will make this as, you know, phenol here having first peroxy linkage here, correct? And then protonation is been done like this. Clear? And internally there is an oxygen here which can attack. So that will attack here and break the bond here, isn't it? Now what is the
Mm.
ring size here? 1, 2, 3, 4, 5. So 5-membered ring will happen here. So like this with oxygen and 5-membered ring like this. Okay. And where the carbon is attacked here, it has one more methyl group on it with the OH group here. So this is a product that should be expected. Is that clear?
Yeah.
So which one is that? C option. Any doubt here, beta, on 17th?
No, sir.
Check out on 18th. OH and Br2 here, Br2 and H2O here. In the first case, what would happen? It is only bromine water. So you will get Br and Br here, correct? So you will get this as phenol having Br here and Br here, like this. Okay.
Yeah.
Second case, you are taking the same bromine in acidic medium. And I told you that when you have it in acidic medium, correct? In the case of acidic medium, what happens? This COOH will go away and that will start creating, you know, ipso substitution. So we will get this as Br, Br and Br. Okay. Now the next question we need to ask is whether this ipso would happen in the first case also or not. Correct. Think about it, whether the ipso will happen in the first case or not, beta. See,
No.
in the first case, how the mechanism is happening. Okay. See, how does the mechanism take place? One second. Oh, bromine in ACOH. Sorry. I made a mistake there. Sorry. Let me show you the mechanism here once. So if you have a phenol here, so first, if you have COOH, bromine first will make Br and Br addition here in the first case here. Okay, correct. Thereafter, see, bromine water is actually acidic water. You will have this as HBr plus HOBr. That is what will be present in bromine water. Okay.
Mm.
So which means if you have this COOH, you just have to remove that COOH. You just have to remove that COOH and bring the hydrogen onto it. Correct? Because in acidic medium, COOH can be removed out. And then if you have this OH here and Br here, correct? Second time again bromination will take place and Br will come here. Okay? So in the X product would be this one. All three bromines, carbon dioxide is been removed here. Correct? But second case, what is happening? Now tell me between benzoic acid and acetic acid, which is more acidic? Benzoic acid.
Enjoy
So
this.
obviously, this acetic acid will not be able to strip this COOH out. Clear? So therefore, this COH will not go in acidic in weak acidic medium like ACOH, but here it was HBr. That's why it was able to
Mm.
do it. Clear, beta?
Okay.
So
Okay.
therefore, here what you will get as one bromine will come here and COH will form, and that's it. Sir, why not second bromine? See, Br2 in acidic medium only if you have it. If you have it in acidic medium, that is sorry, CH3, C double bond O, OH if you have it, correct?
Mm.
This will not easily break into Br plus. It will not easily break into Br plus and Br minus. Okay. Reason being, if at all it will take H plus from here, it will become HBr. HBr is a much stronger acid. Do you think this reaction will proceed towards the stronger acid? No. So that is
No.
why here that reaction will not be proceeded. You will have only one Br, you will have only Br2, which is a mild electrophile now. It will not have a rich amount of Br plus. So therefore, only one particular Br will go and attach on the ortho position, whichever it is open position. Clear, beta?
Okay. Yeah.
So what do we get?
So,
Only B in this case. Okay.
yeah.
What is a major product in the following series? See, first one here with sulfonation. When you do sulfonation here, what do we expect? We'll get this as SO3H, because
Yeah.
if you check out, the temperature is given as 100 degrees, so TCP is favorable. Hmm.
Mm.
For sulfonation, para is TCP.
Yeah.
Thereafter, chlorination is been done, so which means at ortho position you will get one chlorine here. SO3H will be present, and then
Mm.
you are reacting with dilute H2SO4 and heat, which will favor desulfonation and ipso substitution. So you will get this as OH, H, and Cl. So what do we get? We are getting chlorophenol, isn't it? Acha, this can happen two times depending upon how much moles you are giving. So go with the options given. Clear?
Okay.
So which is the best option possible here? C.
Mm.
Clear, beta?
Yes,
Right.
sir.
See, next one. Phenol, when you react with acid chloride, first an ester formation, because any
Yeah.
acidic group will make it into an ester form here.
That's the.
So ET here. This is the product you will get. Okay. Then we have HCHO, HCl, ZnCl2. Okay. Now, here what do we get here? Is CH, HC. Then we have let me write it this way. HC double bond OH we have. So here we'll have plus charge this way, and that H plus will come from HCl in the presence of ZnCl2. Okay.
Okay.
So this is an electrophile that we have generated. So now this is a donating group, right? Oxygen will be still activating the benzene. So from the para position, it will attack on the carbon. So from the para position, it will attack on the carbon, and due to which we will get this as O C double bond OET, and then this will be CH2OH. Okay.
Yeah.
And thereafter further hydrolysis is being done. On hydrolysis again, this will as ester will break into phenol and acetic acid. So EtCOOH. So what is the final product you will have? This one. So which is option B. Any doubt?
Yes. No, no, I got it.
Right. C21. Which of the following reactions will not result in the formation of anisole? Okay. First one is like a basic um, Williamson ether synthesis. It
Yeah.
will attack here, sulfate will be pushed out. So we will get 2 moles of anisole. We'll get 2 moles of anisole, OCH3, and you will get Na2SO4. This is the product form. Second, in this case, second case, right? Uh, Same logic here. Lone pair from
Yeah.
here will attack. I minus will go. So we'll get this as PHOCH3. Correct. Next, third case also CH2 minus N2 plus this is. First, this will take H plus,
Yeah.
converts into PHO minus. with CH3 N2 plus. N2 is a good leaving group. This will attack via SN2 mechanism. Again, you will get anisole. Last case, here CH2 minus will take H plus from here. You will get phenoxide ion plus CH4 gas. CH4 has already escaped. So do you think anything will be formed here? Nothing. So here anisole is not formed. Okay.
Okay.
So I suppose this part is clear, beta.
Yes, yes.
Right. So I gave you some basic questions, what need to be done, correct? Rest of the questions, I think you should be able to do it. Okay. Try multiple correct as well as two matrix matches which are there. Okay. This is
Yes, sir.
only based on phenols. Now you will have an assignment collectively which will have alcohols, ethers, phenols, and their mixed questions as well. Okay. Right.
Okay.